Good day, I'm Maile Madziba. Welcome back to our channel. Today we continue with class test 3 of our CIR 123, which is the second chemical engineering module at the University of Pretoria. We are looking at part 4 of class test 3, and this is actually the 2011 version of class test 3. So we did A, B, and C of the class test, and now we are looking at the last part, which is D, and it says if the product gas mixture CO and H2 is at 30 degrees Fahrenheit and 150 kilopascals absolute, what is the density of the gas mixture in kilograms per meter cubed? Also, what is the flow rate of the stream in normal meter cubed per hour? So basically, what they are saying is that if this product stream here is actually 30 degrees Fahrenheit in temperature and also 150 kilopascals absolute pressure, what is the density of the stream? So if we're going to be able to get the density, we're going to need the composition of the stream. So, and also the second question says, what is the flow rate of the stream? So it's also important that I explain the nm cubed per hour, that it shouldn't confuse one in appearing to be like Newton meter cubed per hour. It's actually normal meter cubed per hour, so it's nothing big. And because this second part is actually shorter, we're going to start with the second part, which is calculating the flow rate of the stream in normal meter cubed per hour. So if we're going to do that, we're also going to need to get the composition of stream D, and we did calculate stream B and C, and we know very well that we have the composition of B. And just to bring back the work that we did in the previous part, so stream B, we know that the CO and the H2 and the CH3H14 and the C6H14 and the CH3OH, right? So this is actually the composition of stream B, but we are told that in the separator here, all of C6H14 and CH3OH actually gets to be condensed into liquids, and only CO and H2 is actually allowed to pass. So, and we are told that it's actually pure CO and H2, which means none of C6H14 and CH3OH do come here. So this tells us very well that the composition of D is actually CO and H2, and we did calculate that here. So just to put it down, so I can just say D, stream D is equals to 21.35 kilomole per hour, right, of CO, right, and also 42.7 kilomole per hour of H2. So this is basically stream D. Let me write here. This is basically the composition of stream D, and we can just say stream D total is equals to, if you use your calculator, you'll find stream D is 64.05 kilomole per hour. So now we know that the total of gas in here is actually 64.05 kilomole per hour. And if you're going to be calculating the flow rate at NTP, or the flow rate in normal meter cubed, we're going to need to multiply the flow rate in kilomole per hour with a constant of 22.41. So let me just write that. Let me just say flow rate at NTP, that is normal temperature and pressure, is equals to 64.05 kilomole per hour multiplied by a constant of 22.41, right? This constant can have units, many different units, depending on the set of units you use. So it can be, for example, liters per mole, and it can also be meter cubed per kilomole. So in our case, we're going to need, because we're working with kilomole, we're going to need the meter cubed per kilomole. So I'm gonna use those units per kilomole, right? Yeah, so it's important to understand that the liters per mole is just, or rather meter cubed per kilomole is just 1000 times, not totally 1000 times. If you're going to move from liters per mole, you just need to multiply 1000 over 1000 and then you move to meter cube per kilomole. So it shouldn't be that complicated. And then if you use your calculator, it gives you 1435, right, meter cubed per hour. This is because if you can check here, the kilomole cancels out and you are left with meter cube per hour. Now what about the n? The n is just to show that it's actually at NTP, so you can just put it there. It's not something that you really need to calculate. You can just put n meter cubed just to show that it's actually the flow rate at normal temperature and pressure. So this wraps up the second question, which says calculate the flow rate in meter cubed. And this takes us to this question there, that what is the density of the gas mixture? So before we go far, I just need to write down the equation for calculating density. So the equation for calculating density is rho equals to Pm all over RT, right? So this is actually the equation that we're going to be using to calculate the density. And if we look at this equation, we realize that we need pressure. We need this M here is actually the molar mass, or the average molar mass if it's actually a mixture of gases. And then we have R, which is a constant. And then we have T, which is the temperature. Now, when we look at the information we are given, we have the pressure. We are told it's 150 kilopascals absolute. And we know very well that this equation works with absolute pressure. And the molar mass, we don't have, the average molar mass we don't have of the mixture. So the first thing we're going to need to do is to calculate the average molar mass, and the constant we don't need to calculate. And also it's important to understand that the temperature we are given in degrees Fahrenheit, but this equation needs it in Kelvin. So another thing we're going to need to do is to convert the 30 degrees Fahrenheit into Kelvin. So this takes us to our step one. I can just say step one, right? So step one, calculate the average molar mass. Calculate the average molar mass, right? So this is what we're going to be doing. And if we're going to calculate the average molar mass, let me just write the equation of the average molar mass. I'm going to write an equation that is going to be used specifically for this too. So the equation of the average molar mass is going to be the mole fraction of CO, right, multiplied by the molar mass of CO, right, plus the mole fraction of H2 multiplied by the molar mass of H2, right? This is because we have two gases that have mixed together. So with that said, if you look at here, we realize that we need the mole fraction of CO, we need the mole fraction of H2. The molar mass of CO and H2 is nothing big. So moving forward, then we're going to need to calculate the mole fraction of both these two. And I'll do just that. I'll just say mole fraction of CO is equals to, right? Let me just do it straight. Or let me say moles of CO over total moles, right? So it's going to be the number of moles of CO. It's actually it's 21.35, right? It's 21.35 kilomole per hour. All over the total, it's 64.05 kilomole per hour. So if you use your calculator, you find that this becomes 0.3333. So it's 0.3, it becomes 0.3333. So, and then now the mole fraction of H2 is equals to the mole of H2, number of moles of H2 over the total number of moles, right, total moles. So if you do that, H2, let me write this properly, total mole. So if you do that, the H2 we find it to be 42.7, right? Yeah, 42.7 kilomole per hour, all over the total is 64.05 kilomole per hour. And if you use your calculator, you'll find that it gives you 0.6667. So that is basically the mole fractions of both. Now if we are able to get the mole fraction of both, it's easy to go back to the equation and calculate the average molar mass of this gas stream here. And when we've done that, we can then go back to the equation with that. So with that said, we can just say therefore molar mass average is equals to the mole fraction of CO 0.3333 multiplied by the molar mass of CO. The molar mass of CO is 28. It's 16 plus 12, so it's 28, right? Plus the mole fraction of H2 is 0.6667 multiplied by the molar mass of H2, which is 2, and if you use your calculator, it gives you 10.67 kilograms per kilomole. So this is actually the molar mass of the mixed gas stream here of D. So now bringing back the equation, we know now we have the pressure, we have the average molar mass, we have the R that we know is a constant, and we have the T. This then takes us to our step 2, where we're going to need to convert the T from 30 degrees Fahrenheit into Kelvin. So step 1 is done. We go to step 2. Step 2, convert 30 degrees Fahrenheit into Kelvin, right? And if you do that, just to write the equation for converting degrees Fahrenheit into Kelvin is T in Kelvin is equals to T minus 32, right? Multiply by 5/9 plus 273.15, right? And let me just highlight here that where T, small letter T, is temperature in degrees Fahrenheit. So basically, I'm trying to explain that this is the equation where the small letter T here is the temperature in degrees Fahrenheit. So with that said, we can just say, therefore, T in Kelvin is equals to, T here is 30, so we are told that it's 30 minus 32 multiplied by 5/9 plus 273.15, right? If you use your calculator, that's going to give you 272.04 Kelvin. So now we have managed to convert the 30 degrees Fahrenheit into Kelvin. This wraps up our step 2, and it takes us to our step 3. Step 3. In step 3, we then calculate rho, which is our density. Calculate the density, right? So we say, therefore, let me write in bracket, calculate density, right? Therefore, rho is equals to PM over RT is equals to the pressure. We already given that it's actually 150. What? Oh, the pressure we are given it to be 150. Let me just write it properly. 150 kilopascals, and absolute multiply by the average molar mass. We did calculate it to be 10.67 all over our R. It's actually a constant of 8.314 multiplied by our temperature in Kelvin is 272.04. If you use your calculator, it gives you 0.708 kilograms per meter cubed. This then becomes our density, or the density of the gas stream here. So under the conditions that the temperature is 30 degrees Fahrenheit and the pressure it's actually 150 kilopascals absolute. So this brings us to the end of part 4 of our class test 3, and also that wraps up class test 3. Thank you for your time, and I hope we meet again in our next video.